Differential equations, we're looking at section 3.2, part 2. You can see at the bottom of the screen, we're trying to solve for p. So tell you what, just as we continue, how about we just go ahead and take a reciprocal if two fractions are equal? Well, then their reciprocals, their flips have to be equal. And then what? Well, if you want to get p by itself, you multiply by a. And that's where we come right over here. So this is really what we get is we solved a logistic differential equation. And we are solving for p. So this can be very, very helpful down the road as we're looking to actually, solve and get, p alone. Look, just another thing that we'd like to quickly comment on. If we were to go back to this green equation right here, just want to bring something to your attention. If we let t equal 0, well, you can see that, this right-hand side would just become e to the 0, which is a 1. We'd get, a constant. We'd get this c1 e to the at. But remember, at t equals 0, that's really the beginning population. So that's super, super helpful. What we can do is say, hey, C1 is equal to e to the AT. And, pardon me, as this e to the 0, so sorry, is going to be a 1. As we have that would allow us to find what that constant is. So obviously e to the a times 0 is going to become a 1. So how does that help us? Well, here's how. Right now we can come back and we can say, hey, look at this equation in blue. But look what we just found. We found out what C sub 1 really is. So we're going to be able to do this. We can say, that P is equal to, well, A times C1. Well, this C1 is this very ugly looking expression right here. And then we're going to say divide that by B times our C1. Well, guess what? We found out what our C1 was. It's this very ugly expression that we just found in blue. And then we'll say plus e to the negative AT. Well, where are we going with this? As you're looking here, undoubtedly this is a very ugly, messy kind of a fraction, and what's making this super ugly are these a minus b p naught. So I'm going to multiply the top and the bottom by this same thing. I'm really just multiplying by a 1 when I do that. And as you multiply, these are going to cross out. And then we're going to have to distribute over here. And what are we going to be left with? Well, finally, this is our last form right here that we'd like to call attention to. Look at this numerator. It's just a times p naught. That's what we have here. Down below, this a minus b p naught is going to cancel out. You just have a b p naught. And then finally, you have this e to the negative AT times that parenthesis right there. That's really what you've got. So it's an altered form of the population function. And what's so nice about that is you're now going to be able to have a beginning population there. So we're going to finish up this lesson right now, really revisiting these equations that we've developed here, and we're going to put them into use in a problem that might not seem like it's logistic growth, and yet it truly is. Suppose that a student carrying a virus returns to an isolated college campus of 1,000 students. If it is assumed that the rate at which the virus spreads is proportional to not only the number X of infected students, but also to the number of students not infected. By the way, if the number of infected students are going to be X, not affected, remember you get 1,000, that's 1,000 minus X, wouldn't it? So we've got that proportional situation right there. And we'd like to determine the number of infected students after 6 days if it is further observed that after 4 days, 50 students are infected. Well, here's really what we can make use of. This is, in fact, logistic growth. Here's what I'd really like to call to your attention here. And, instead of having an X, maybe we'll have a P. How about that? As you're looking at this, M is your maximum carrying capacity. You've got 1,000 students here. We could say dP dt is Kp times 1,000 minus P. Look at that. And right now, as you're looking at this, we're going to do something maybe you might be a little surprised at. I'd recommend that we distribute that K in there. And why are we doing that? We'd have P times 1,000 K minus Kp. And it's right here that I'd like to have a little bit of a flashback to what we had earlier. I'm talking about this right here, where we had our first page, that dP dt. You can see what we wrote off to the side here. dP dt was equal to P times A minus BP. And why is that so important? Well, now you can make a comparison between these two parentheses here. You can say, so this would mean that your A is equal to 1,000 K. It means that your B, the number in front of K, is in front of P, is going to be a K. And by the way, what we're assuming in this problem is an infected student comes in, so your beginning number of infected people is just a 1. So we're going to come back right now and see if we could use this very last equation that we were working with just previously and see if maybe that could come and help us out. So let's just recopy that and say, look, we've got P is equal to A, P naught, down here is B, P naught plus A minus B, P naught, e to the negative AT. And here's where we can say, hey, now I know what my A is, and I know what my B is, and so forth, and I actually know what P naught is. So I can say P is equal to 1,000 K, that's my A, times a 1. Down below, my B is a K, my P naught is a 1, plus, well, this would be 1,000 K minus a K times a 1 times e to the negative, well, what's my A again? Well, it's 1,000 K times a T. And here's the nice part. I do just want to call this to your attention. We're going to have 1,000 K up here. Down below, we'll have a K plus, well, this right here is 999K times e to the negative 1,000 KT. And I think at first glance we look at this and maybe we're not immediately impressed that, we did this. It's looking a little bit better. But guys, you can divide out a K everywhere. You can divide out that K. And very quickly, let me just recopy that up here. You're going to have P is equal to 1,000 all over a 1 plus 999 e to the negative 1,000 kt. So it's at this point where we practically have a population equation. You might notice we don't have that k just yet. Guys, I do want to point out that we're trying to find the number of infected students after 6 days, but you have an initial condition. When t is equal to 4, they're telling you that 50 students now have that virus. So let's go ahead and just put 50 in here, and we'll have 1 plus 999 e to the negative 1,000 times k times a 4. I hope you can see quickly 1,000 times 4 is just negative 4,000. And we'll have negative 4,000 k. Now, we can go ahead and solve this a number of different ways. We could even solve it by hand. With the TI-89, you can use the solve. You can type in an equation, whatever the equation is, and then you'd have your variable. You could let your k be an x and so forth, and you could even hit a green diamond to get an approximation. You could solve this by hand. You could solve it graphically. For the sake of time, I just want to tell you I already did that, and I got 0.000991. Just trying to speed this up so that we can move a little bit more quickly. But as we're wrapping this up, what does that really mean? Well, now you can come back to this equation right here and get P is equal to a 1,000, and we'll have 1 plus 999. If you multiply negative 1,000 to this k, your decimal will go 1, 2, 3. It's also going to be something negative. So you'd have an e to the negative 0.991t, roughly. And then they want you to find out what's happening on day 6. You could just type in a t equals 6 and get an estimate. I will leave it up to you to check that this is correct, that you would get about 277 students. Okay, best of luck. Thankfully, you're not going to be rederiving the logistic equation. You're rather going to be solving and working it through much the way we just did with this example. There are a couple other variations at the end. Sometimes they will give this to you. Harvest and restocking, they might, give you an additional plus h. Gompert's differential equation, some students might be interested in actuarial science or even in cancer research, like with growth of tumors and mathematical applications in biology, biomathematics. Things like that can definitely have applications as well.